All right, thanks for coming out today to listen to this talk. I'm going to be talking about Swift's numeric types and protocols. We have a lot to get through, so I'm going to try to go fast and not go over. We have a lot to discuss, not just the types and protocols. We're going to look at their implementation, and we're going to look at floating point precision. Ultimately, this talk is about numbers and how they work. And we can describe the natural world in the language of mathematics, but in computing, this is actually much more difficult. We have a lot of constraints. And so to kind of ground this, numeric types are pretty fundamental to computing in general. I mean, computers used to be the size of a room, and they're basically just giant calculators, the ENIAC, the electronic numerical integrator and computer, aka a calculator. Was used for a lot of different things in terms of just big computations that took humans hours and hours to do. Now all of this is condensed into calculator.app, which is everyone's favorite. So this is a breakdown of Swift's numeric types. We have three basic categories. We have our floating point types, our integers and unsigned integers. Int and uint are special. They default to the platform native word size. So if you use an int and you're on a 32-bit device, it'll be an int 32. If you're on a 64-bit device, it'll be an int 64. And so you may be wondering, like, why do we even have all these types? Why can't we just have int and double and be done with it? Well, obviously there are different, the immediate answer there is that there are different processor architectures. This has changed over time. Now we have mostly 64-bit devices, still some 32-bit devices lying around. Specifically with Swift, we still have to interop with C APIs. When we have an array of bytes that gets bridged over, we actually receive that in Swift as a tuple of int 8s. And for other things like SQLite or core data, you may need to store specific numeric sizes in there, like an int 8 or something. And Swift isn't really used in like embedded systems programming yet, but if Chris Latner achieves his goal, one day it will be. So before Swift 3 and 4, it was like pretty difficult to work with numeric types. Floating point didn't even have all of the like IEEE features. The language in general was just like pretty rough around the edges, very mature. We can see that with the previous kind of hierarchy. There's this weird disallowable mixed sign numeric protocol. It's like, what does that even mean? You see these underscores, those are like, quote, private protocols because you couldn't really express certain things in Swift itself. So there are all these like weird things in the standard library. This other view, we have this like absolute valuable protocol. Again, what does that even mean? And float 80 didn't even conform to the floating point type protocol, so everything was working great. And then Swift evolution happened, which is everyone's favorite, and we got these three great proposals that really refined the APIs in the standard library. We got better naming for these protocols. The arithmetic protocol disappeared, and we got a much more refined hierarchy. And now it looks like this. So we have our top level numeric type that breaks down into signed numeric. Then we have our integer and floating point protocols. So we're going to kind of go through each of these, see what each one provides, and then move on to some more stuff. So numeric, we get our basic operators there. We can use this in our own code by defining, let's say, this extension on sequence. We have an array of numeric types, and we can sum them up. Very simple. Signed numeric adds this notion of signedness to values. So floats and ints can be signed. This obviously excludes unsigned integer types. Similarly, we can write an extension to like filter out negatives from an array. And it's great because this will work with everything that inherits from numeric. Next, this brings us to binary integer. We get more arithmetic, bitwise, and bit shifting operators here that specifically operate on integer types. We also get a lot of conversion APIs, so we can construct different ints with different sizes, optionally converting or truncating bits as needed. There are also some unsafe APIs, and this also allows us to compare across integer types. The binary integer protocol unifies all of those integer types such that we can compare them without getting compiler warnings. So next, that brings us to fixed width integer, and we can start to see more of the properties of how these numeric types actually work, how they're represented in memory. This adds the notion of endianness. We get the type bounds and the bit widths of these integers. So this protocol defines our min and max, and so if we say int 16 min and max, int 32 min and max, it's specific to that type. Endianness, if you're not familiar, is the order of bytes. Little endian, which is probably the most common for architectures. The bytes are like what we would consider in order. Big endian, byte swap, we can see that we just flip those bytes. And we can write some cool extensions on fixed width integer. This computed property will just iterate over the bytes in any integer of any size and convert it to the binary string representation. So you can see down here, if we create this int 16, and we can see the binary string representation. Again, this is cool because every single int type this will work for. So this brings us to floating points. And obviously, floating points are our fractional numbers. The floating point protocol provides all the features of the IEEE spec. We can write a function like this to compute the hypotenuse of a triangle and constrain that based on the floating point type. We'll look at this more a little bit later. The floating point protocol also provides common constants. So we have least normal magnitude and greatest finite magnitude. This is equivalent to like float min or float max, but in Swift 4 they have been renamed. Again, this lives on the protocol, so then each specific type, you get the precision of that type. So even the constant pi, if you call this Float.pi, you'll get 32 bits of precision for pi. Otherwise, you will get, if you call double.pi, you'll get 64 bits of precision for that constant. And this brings us to the binary floating point protocol, which is what all of the numeric types most immediately inherit from. So float double and float 80. And this just provides the specific radix 2 floating point type. So radix, or your base, binary is base 2, decimal is base 10. So this means in the future, the standard library could add a decimal floating point protocol, and we could have a decimal type in the standard library. And then it also opens up this idea that you can create your own. You could do this octal floating point protocol if you wanted. I don't recommend that. There's probably no use for that other than like an academic exercise. But all of this kind of brings us to this conclusion that protocols aren't just bags of syntax. We're not just grouping syntactic things together. They have very clear semantics, and we can see how this breaks down. Every protocol has a clear delineation of the semantics of what it's trying to provide. But even though we have these protocol-oriented numerics, unfortunately, we still have to work with concrete types very often. we see all these different compiler warnings when we try to mix types. So if we try to add an int and a double, Swift complains, I don't know how to do this. How do you add an int and a double together? If we try to add a float and a double, well, they're both floating point types. Still can't do it. But down here, this last example, this works. We're adding a double and an integer, or at least it seems that way. What's actually happening there is that 42 is getting promoted to a double. Swift's type inference infers it as a double. Doubles are also, they also conform to the expressible by integer literal protocol. And so Swift just assumes, oh, what you meant here was a double. If you intended to truncate this, you'd need to still explicitly cast. But the reason this happens is that Swift has no way to guarantee, it doesn't know what you want to do. It can't just magically infer that, oh, you wanted z to be an int here. So it does the most reasonable thing it can. If we go back to our previous examples, they start to break down when we mix numeric types. So we had this filter negatives function, and once we start mixing types in that array, Swift complains, oh, this is ambiguous. I don't know what you mean. Same with our floating point example, this hypotenuse function. If we pass a explicit double and an explicit float, again, Swift complains, I don't know what you want me to do here. So it's pretty sad. However, writing a function like this, it's generic over T, constrained by the floating point protocol. It's still way better than writing 4 of this function for every specific type. So it's a little bit better. So when we're dealing with concrete types, you may be asking yourself, well, how many bits do I need? Which of these types should I use? And really, the thing to do is just use int and double. This is what the Swift programming language book recommends. If you default to using these values, unless you have a very specific reason not to, some of those we discussed earlier, you should let type inference do its magic, let the Swift compiler infer what you mean, and you can reduce or completely avoid all of this constant casting. So how can we how can we write extensions on these numeric protocols to make our calculation code more expressive? We're going to look at a small example here just to kind of illustrate ways that I think we can write much better code. So if we take this example, let's say we're drawing some line graphs. Maybe you're making a stocks app and you want to show the price over time, or you're making a pedometer app because we don't have enough of those. Then let's say we have our points, we calculate the slope, and the slope has 4 cases, right? It can be undefined if it's a vertical line, it can be flat or positive or negative. We can write a few extensions on these different protocols for our specific domain here. If a slope is undefined, that would be we've computed that it is not a number, and positive and negative are straightforward. Here, this extension actually works on every single numeric type. So if you call this on an integer type, the 0 is inferred as an integer, but if you call it on a float or a double, that 0 gets lifted into a float or a double. So it works everywhere. You couldn't do something like this before. It'd be much more difficult. And so we end up with something like this. Is0 is actually defined on the floating point protocol. To me, this reads much better than using equals equals 0, or slope is less than 0, or slope is greater than 0. This code really reads like a sentence. You don't need any comments. It's very clear what's happening. And a year from now, you know what this code is trying to do. And this is just a small example of how these small tweaks in our code can really make a big difference in readability. But you know, you can You can probably find examples in your own code of how to improve these things. So let's kind of switch gears a little bit. Like most types in the standard library, the numeric types are structs, so they're primitive values, but unlike C and Objective-C, where we have lowercase I int, in Swift we have capital I int. They're much more powerful. So as Greg Heo would say, let's go one more level down. So how are these types implemented? Well, everything is open source. We can go on GitHub. We can look at the standard library. We can see that all these structs have a private value property. It's a built-in type. We'll discuss that in a minute. First, we need to briefly review how the Swift compiler works. It's built on top of LLVM. So we begin with our Swift code that gets parsed. We create an abstract syntax tree that gets transformed into Swift intermediate language, which then gets transformed into LLVM intermediate representation. That gets handed off to an LLVM backend to generate the binary for whatever platform you are targeting, PowerPC, x86, whatever. So we won't look at all of these. We'll just look at a few types here. So we look at int64. We can see the value. The underlying value is a built-in int64. So the standard library is written in Swift, but it's a little bit special because it has access to these built-ins, these built-in types, which basically they map directly to primitive types in LLVM IR. So any language that's written on top of the LLVM compiler architecture eventually transforms into LLVM IR, and this is how Swift kind of directly accesses that. Again, with int8, we can see we're using the built-in int8. We can look at float. We see our built-in FP floating point IEEE 32-bit value. We can construct this from our literal values. We can even construct it from a 64-bit value. And then these functions convert the bits and set the value directly. Slightly more interesting, we can see what happens when we try to construct an int64 from a double. So we have all these precondition assertions here that we aren't overflowing or underflowing this integer. And this is because Swift is a memory-safe language. Not only do we guarantee type safety, but Swift guarantees the boundaries on numeric types. It'll trap on overflow and underflow, and we can see that in the source. We can look at our code and we can see this happen. If we try to initialize an int8 with a number that's too big to be represented in a single byte, Swift will complain. We can't represent negatives in a uint. And if we try to initialize an integer with the equivalent of double max, Swift complains, oh, this is way too big. The result would be greater than int max. However, if we take float 80, the largest float, has over twice as many bits of precision as float 32, which is just a type alias for float in the standard library. We don't get any exceptions. There's no precondition check in the source code. We just get infinity. It's kind of weird. So let's take a quick quiz. What's the value of sum in this case? So we start with sum, it's 0, it's exactly 0. We have 0.1, we're going to add it 10 times. So add 1/10 10 times. 1.0? 0.999. Lots of guesses, yeah. It's not 1.0. That's for sure. It's 1.00119, all these garbage numbers here. Floating point math is not exact. So what's happening here? Thank God for Greg Keogh. We need to go one more level down again. So we're going to talk about floating point precision. But before we do that, we actually need to talk about memory layout because nothing's going to make sense if we don't understand that. So integers are easy. We just take some bits, we shove them in there, and everything works out. Couple caveats. Signed integers are represented in 2's complement, but that's just an implementation detail. All we really need to know is you have some bits, and then we can see the binary representation, we can see the decimal representation of that. It's very straightforward. But floating point values are not that simple. They have 4 different elements. We have a sign, we have a radix or the base, so again, binary is base 2, decimal is base 10. We have the significand, so this is the number of digits of that base, and then we have our exponent, which is the offset. And the exponent is biased, and we'll discuss what that means later. So to compute any floating point value, what you have to do is you take the significand, you multiply it by the base raised to that exponent. And how convenient. The floating point protocol provides all of these components for us. The Swift standard library is just really great for exploring these types and how they're implemented under the hood. So floating point values are not just bits. We have our leading single bit for our sign. We have our 8 bits for the exponent, and then the remaining 23 bits for the significand. And this bias, the bias in the exponent is 127. This makes it easier to store signed values. So any exponent that you have, you subtract 127 to get the actual exponent value. So we can look at the representation of pi, everyone's favorite number and dessert. And we can see sign, the sign is positive here, so it's a 0. Look at our exponent. What's broken down here is the decimal representation, the bit pattern, and then the binary representation. So it's 128, but if we subtract that bias of 127, we get 1, so that's 2 raised to the 1. Our significand, 1.57. And if we compute that at the bottom here, the 1.57 times 2 raised to the 1 exponent, and we get 3.14. So we can use the standard library protocols to also examine this further. We can compute this in our Swift code exactly, get all the same values. The binary floating point protocol further extends this. We can check the raw bit patterns and even the bit counts of each of these components. So again, everything checks out. Our bit patterns, these bit counts are constant, obviously, for double types. You have more bits for the exponent and significand. It varies a little bit, but you still just have that single bit for the sign. Also, the base or the radix. Obviously, this is 2 because we're in binary. There's no bit to store this information because it's implicit. We don't need to waste that space. So this layout leads to some interesting properties, or more like artifacts. There's no such thing as signed 0. That does not exist in math. 0 is a special number. It's not positive. It's not negative. But in computing, we can have positive and negative 0. So this is represented as zeros across the board, but then we still have this sign bit. So luckily, the IEEE spec defines positive and negative 0 to be equal to one another. Otherwise, we'd have ridiculous bugs. Yeah, and we can look at the implementation in the standard library. And it's pretty cool because all it's doing is comparing the bit patterns to 0. Not a number. So non is unordered. It's not equal to, greater than, or less than anything, including itself. So never check if something is equal to float.non. It will always be false. You can check is non to determine that. And again, we can look at the implementation. all we're doing is comparing the bit patterns. Is finite is another property, but I've defined it here. It just checks the bit pattern for the infinity exponent, which is, again, another constant, which is just all ones for the exponent. Again, the significand is all ones here, and that is how we represent non. The last one that's interesting is infinity. So here, the bit pattern, we have all ones for the exponent, we have all zeros for the significand, and we can see that we construct this with this float initializer. We give it the sign, we give it the bit patterns, and construct infinity. Okay, now that everyone is an expert on floating point layout, let's get back to precision. So what we've seen in our previous examples is that floating point values are imprecise because we have to round. And you hear this in your CS 101 class. We know that floating point numbers are imprecise. We always have to round them. But how do we measure this rounding error? You may reach for float epsilon. That's common. It's a C macro. But if you try to use this in Swift 4, you'll get an error. Float epsilon is deprecated. You need to use ULP of 1. What the hell is ULP of 1? Let's read the documentation. The unit in the last place of 1.0. Sweet. So, all right, we're good. Talk's over. No. What does that even mean? We can read the discussion, the positive difference between 1.0 and the next greater representable number. Okay, so we're talking about what is representable. We know we have to round, so there are some limitations here in the numbers that we can represent. And it says this is equivalent to float epsilon or double epsilon. Okay, well, it's also referred to as machine epsilon sometimes. We can look at the ISO-C standard and see how this is defined. These are the constants. We can check it in Swift. Everything checks out. Okay, so it's the equivalent of float epsilon. That tells us something, maybe. It's these numbers, okay? But if we look a little further in the docs, right next to ULP of 1, we'll see ULP. But this isn't a constant. It's not static. It's a computed property. So you can say 1.0.ULP, 3.456.ULP. What does that even mean? Okay, ULP stands for unit in the last place or unit of least precision. So it measures the distance from a value to the next representable value. So just like ULP of 1, it was measuring the distance between 1 and the next greater representable number. This is for any value. So to understand this, let's consider the integers first. So we have this number line. We're bounded by int min and int max. We can't go past those. But every single number is uniformly distributed. We know that to get from 0 to 1, we just add 1. From 1 to 2, we add 1, and so on. Every number, the next representable number is always 1 away. Integers are exact. So we don't need any notion of ULP for integers. This is why it doesn't exist for integers. But floats, not so much. As we've seen, they're very difficult to represent in bits. It's not just bits. We have this specific format. We have to divide these bits up into these different components. So the next representable float, it's unclear, especially when you consider irrational numbers. They repeat forever. So if a decimal is repeating forever, what's the distance from that decimal to another decimal that repeats forever? Let's talk a little bit about number theory. So we're modeling the real numbers here. We have our rationals and our irrationals. Irrational numbers repeat forever, like pi. We have our integers, we have our natural numbers, and Swift's numeric types fit into this world like this. So our floats and doubles, they can represent all of these rational and irrational numbers, all these fractional numbers. Integers and unsigned integers are much easier to reason about. But the problem is that between any two floating point values, there are an infinite number of values between them. So like we said for integers, we're bounded by int min and int max, so we can't extend beyond those, but within that bound of int min and int max, we have a finite number of representable integers. That's not true for floating point values, because even between 0 and 1, there are an infinite set of fractional numbers between 0 and 1. In fact, it's more than the entire set of integers. But we only have 32 bits. So we have to round because these values cannot be represented. It's impossible. We don't have enough bits to represent these fractional values between all of these decimals. And this is why we need ULP. So if we go back to this quiz, every time we're adding here is an opportunity for rounding error. We're adding 0.1 10 times, so every time we're rounding and accumulating error. And we get this number, and what we said was garbage before, but it's actually not. If we look at the ULP of 1.0, it is that exact decimal. Is this real life? Yes, it is. So we can see in practice this error accumulating. It's this rounding error. So let's define what ULP actually is. So we take our machine epsilon value, that's our ULP of 1, our float epsilon, multiply that times our base, and raise it to the exponent of the value. Remember, the exponent is the offset, so this makes sense. We're measuring the distance from one value to the next representable value. And we can compute this in our code. So we take the ULP of 1, raised to the power of the exponent from our base, and we can see all this checks out. If we check the value that the standard library provides, value.ulp, we get the same as what we just computed. This leads us to actually accessing that next representable value. So the floating point protocol provides nextUp, which is that next value. And intuitively, we can imagine, okay, well, if ULP is the distance between the current value and the next value, then if we just add ULP to that value, we should get what nextUp is equal to. And that's exactly what we see. But this precision varies. The larger a value, the less precise it is. So the ULP of 1 is quite small. It's float epsilon. But the ULP of a billion, 64. This means comparing floating point values is not very straightforward. It's actually quite hard to compare values exactly. There's some rules of thumb here for how you're comparing against, values and what you should use. You never want to use float epsilon or ULP of 1 as a tolerance for a comparison. So just a few more slides here. If we, so the best way to do this is to compare the relative ULPs. So the relative units in the last place. So adjacent floats have integer representations that are also adjacent. So let's assume that 1.0 and 2.0, they're next to each other. Then the bit patterns for those integer 1 and 2 should be the same. So we can actually just copy the bits from our floating point value into an integer. Swift lets us do that pretty easily. We can access the bit pattern and create an int32 from that bit pattern. There are some edge cases to handle here, but we'll keep this simpler. And so we can compare using these relative ULP values. So let's say we take the value of 1,000,000. If we add the ULP of that value times 5, so we're adding 5 ULPs to that value. We take the absolute value of our original value and what we computed. We get the integer representation, and we can see that the absolute value here is 5. So we're 5 ULPs away. So from 1,000,000 to 1,000,000.3125, it's 5 representable values later. So when we're using comparisons like this, if the ULP, if that absolute value there is 0, that means we have the exact same floating point representation. If we're 1, if the absolute value there is 1, that means we're exactly 1 float away from what is possible to represent, which means they're as close as they can possibly be without being equal. So if we have less than or equal to 1 ULP, we can consider those values equal. So to kind of sum up here, basically precision is hard, equality is harder, and the Swift Standard Library really provides great APIs for us to examine these layouts and how floating point numbers work. I encourage you to open a playground and play around with this stuff. It's pretty interesting. There's some resources here if you want to read further. These slides will be online. And that's all I have for today.
Thank you, Jesse, for the really insightful talk about numbers in Swift.